Yes.
Yeah.
Yeah.
So I think what Isaac was talking about was around here. So Isaac, can you see the statement here?
Yes,
You're the one who had asked me. Yes. It's actually given in the notes. What coprime means is M is invertible if the GCD of M and N is 1. That's what it means, coprime. So I will go to the next topic. That's homomorphism. So now we've learned about groups. We want to see how can we relate groups. If you have two different groups, how do we identify them? One way to do it is through these homomorphisms. Now, if you have two groups, G and H, and they may have different binary operations, then a mapping from G to H is said to be a homomorphism if the image of X to Y is the same as the image of X times the image of Y. So if this property is satisfied, then we have a homomorphism. Now this star is the binary operation in G, and here this is a binary operation in H. So you need to keep track of that. So it may happen that you can have a map from a group to itself, and in that case, the binary operation on both ends will be the same. So that can happen as well. So sometimes it's a bit inconvenient to keep writing this star and this symbol, that circular symbol. So it's for the sake of convenience, instead of writing X to Y, we just write XY. And instead of using this symbol for composition, we just omit it and put this the image of X and the image of Y next to each other, like that. So this was the notation we'll use. But most of the time, you need to remember that the binary operation on this end is the one in G, and the binary operation here will be the one in H. So so basically, if you want to prove that a map is a homomorphism, you just need to check this one property. That's the only thing you need to check. That if you pick any two elements, X and Y from G, the image of the product of X and Y would be equal to the product of the image of X and the image of Y under this map file. Are we together?
Yes.
Good. So there are some things we are going to set up now before we continue. First of all, we define the image of a homomorphism. So if you have a map from G to H, the image is just, I think, what you would call the range in your calculus. So every element in G will be mapped onto some element in H. So if you pick all the elements to which the elements of G are mapped, then that set will be the image. Now the image turns out to be, can be the whole of H as well, but it doesn't have to be the whole of H. If it's the whole of H, we usually call the map surjective, but it doesn't have to be the whole of H. Let me admit some people, I think they're trying to join. Okay. So we continue. So now in terms of sets, you can, this is how you will represent it. The image of this map is simply the image of all the elements in G. The set of images for all the elements in G. So pick an X in G, send it to H using the map, and pick up all the elements that we map onto in H. So I think that diagram is clear. And then if you want to write it in terms of a set, this is how you'd write it. And this is a shorthand for indicating the image of a homomorphism. Okay. So if the image is the whole of H, then we say that the homomorphism is surjective. The other word for surjective is onto. So by now you should know it's very important that you have a clear definition of a surjective map and an injective map. So note those down and make sure you look them up again. But if you have problems, you let me know. I can define the concepts. So we have talked of the image. Now we want to talk about the image of a set. So if you have a homomorphism from G to H, you can pick a small set, a subset of H, which we call S, and find all elements in G that are mapped into this subset S. Now this set here will be called the preimage of S. So the set of all elements in G which are mapped to some element in S, that's called the preimage of S. So we use this symbol. It's not really the inverse function because we can use it even when the map is not invertible. It's just used as a symbol to indicate the preimage of a set. So this is not really the inverse of phi. Phi may not even be invertible, but here we use it to denote the preimage of S. And that will be all the elements in G which are mapped to some element in S. Okay. So we now list some classifications of homomorphisms. We have one, if it is bijective, we call it an isomorphism. If it is injective, we call it a monomorphism. Injective means one-to-one. I think if it is surjective, we call it an epimorphism. And if the two groups are the same, if G is equal to H, the map is from G to itself, then it will be called an endomorphism. And if it turns out that the map is from G to itself and it is also bijective, then the map is called an automorphism. So an automorphism is just an isomorphism where the map is from the group to itself. So these two are actually the same. The only difference is now the two groups are the same. Automorphism is the same thing as isomorphism. So the set of automorphism is a subset of all isomorphisms but it's a special case where this domain and the codomain will be the same group. You can still hear me?
Yes.
Yes.
Yes. Yes.
So another definition. Someone whose mic is on, I think you need to mute. So here we have another definition. It says two groups are said to be isomorphic if we can find an isomorphism between them. So essentially, isomorphic groups are considered.
Excuse me, sir.
Yes. Can you read that? So start from the first statement and then move to number 5.
I hope you say yes.
Is it making sense? Yes, bro.
But I heard you said something like it's from G to G.
Yes. It's a map from the group to.
Yes, I wanted you to explain. Yes.
Ask the question.
Yes, I wanted you to explain concerning automorphism. I thought you said it's a set from G to G. From G to G or from G to H?
Now, can you read this first statement? You can read it. It says the map is from G to H. But a special case where H is equal to G, where you have a map from G to itself, and the map is also bijective, will be called an automorphism. Is that making sense?
Okay.
That's what this number 5 says. That's why I'm asking you to read it first. It's important to learn to read.
Okay, thank you.
A lot of these statements, you have to read them over and over again. So if you do that, you have a better chance. They stick. I had shared some handwritten notes. I don't know if you got a copy.
I have not.
So check with your class representative. I think there's a link which takes you to the set of notes which I used for last year's class. And all this information is there. So if you take time and read ahead, I think you will have a better time in class. You already have the notes, and I think you have the time. Just read ahead. And so when you come to class, you will have an easier time. So all this information is in the notes. So
okay, thank you.
So we say that two groups are isomorphic if we can find an isomorphism between them. And if two groups are isomorphic, they're essentially the same. We will see this later, how it works. And once we have an isomorphism between two groups, you can study one group by just studying the other. The properties that one group has will also be in the second group as well, as long as they're isomorphic. So this will be a useful idea as we go along. So we look at some examples of homomorphisms. The first one is this one. We say if G and H are groups with identity elements, E and E prime. So we use E prime for the identity in H, and we use E for the identity in G, right? So if we define a map from G to H by this, we pick every element in G, and all elements in G are sent to the identity in H. Then we can work out the following. If you pick any two elements in G, two elements X and Y in G, then the image of a product of, remember, if you notice here, there is no comma. That's one mistake a lot of you usually make. What is here is usually the binary operation in G. So there is no comma here. Never put commas here. I'm mentioning it because I've seen that happen a lot. So the image of this product of X and Y will be equal to the identity element in H, because this map, whatever you give it, it sends it to the identity element. But now the identity element can be written as E prime multiplied by itself, which is again the same as the image of X and the image of Y. The reason for that is every element is mapped to the identity. And then we can conclude that phi is a homomorphism because it has satisfied this property. This is the only property it needs to satisfy for us to conclude that it is a homomorphism. So that's a trivial example where every element in G is mapped onto the identity element in H. So here we consider the group of real numbers under addition. This is R under addition. And also we consider the group of positive real numbers under multiplication. So these ones also form a group. So we define a map from the real numbers to the positive real numbers as groups by this. We pick any real number and map it X, and we map it to E raised to X. E is the exponent. Now here E is a Euler's constant. This E here is not the same as the E here. Here E stands for the Euler's constant. You know it, the base for the natural logarithm, E. So that's the map we have. So the question is this map a homomorphism? And we can check. So remember the binary operation in R is plus, so we use plus here, X plus Y. Theta of X plus Y would be equal to E raised to X plus Y. And this is the same as EX. This now is from your knowledge of indices for numbers. The same as EX, EY. And this is the same as theta of X multiplied by theta of Y. So now remember the binary operation on this end is multiplication. That's why we are multiplying on this side. So we can conclude it. Yes?
Yes. Question. What is the value of this theta before the X?
Theta is the map. You see, you can use any symbol to represent a map. You must have done this in basic mathematics. Theta, you see the same way I'm using phi. I can use theta, or if you like, if you're not happy with theta, we can use F here. Because F is the F or G or H are more familiar from calculus. But it doesn't matter which symbol you use for a map. You can use any symbol. I've chosen to use the Greek letters. Does that work for you? You've understood? Hello? You know, it's important that you respond so that we...
Yes.
Yes. It makes sense to you completely. So theta is not a value. It's theta represents the map. Theta is not multiplied. It's actually, theta is the function itself. The map that we are talking about, which is now a homomorphism. So we can conclude that theta is a homomorphism because it satisfies this property. We can also make a few more statements about theta. So we observe that if theta x is equal to theta y, then this means that e raised to x is equal to e raised to y. And that means e raised to x minus y is equal to 1. But then this would mean that x minus y is equal to 0. That's the only possibility, which in turn implies that x is equal to y. And that confirms that our map, this should be theta, not phi. So this should be theta because the map we are working with here is theta. So it means theta is injective. So we can also check that for any number you pick, any positive real number you pick, this is always to e raised to natural log of y is equal to y. So the pre-image of y is actually the natural log of y. So any real number you pick from this set, the positive real numbers, it will always have a preimage. That is a natural logarithm of y in the set of real numbers. Right? So for that reason, we can conclude that this map is surjective. So we have checked that this map is a homomorphism. We've confirmed that it is also injective, and we have also checked that it is surjective. Remember, these two are, this should be theta, and this should also be theta. So I will correct that on the notes before I share. So this is theta, and that one is theta. So the map is surjective, and it's also injective, and therefore it is an isomorphism. Again, I have used phi here. It should be theta. So theta is an isomorphism. Does that make sense? Are you?
Yes.
You can hear me, okay?
Yeah, I can hear you.
So this map is an it's an isomorphism. It's one-to-one and onto, and it's also a homomorphism, and therefore it's an isomorphism. Let's see if we can do a few more examples. So here we can consider the general linear group of real numbers with the real valued matrices, and the group of non-zero. R star, remember, is a group of non-zero real numbers under multiplication. Remember when we, so one thing maybe you can do from this set of positive real numbers, you need to convince yourself that it's a group under multiplication. I don't know if we covered it earlier. I don't think we did, but it is a group. These positive real numbers under multiplication forms a group, and you should be able to go back and prove this. So the next example here is we consider the general linear group, the invertible n by n matrices. And we also consider the group of non-zero real numbers. Non-zero means both negative and positive real numbers, except zero, under multiplication. So we define a map from this group to R star, which picks any matrix and sends it to its determinant. So remember, the determinant is a number, so the determinant is in this set, and A is a matrix, so A is from this set. So if you pick any two matrices, now again, this is a problem. It's not R, it should be in the general linear group. A and B should be from the general linear group, not from R. Looks like I made quite a few mistakes in the notes. I will correct this before I share them. So for all A and B in the general linear group, we can find the image of the product of A and B, which will just be the determinant of A and B, because what this map does is whatever you give it, it gets the determinant. So if you give it the product of A and B, it will try to get the determinant of A and B. And from the properties of the determinants of matrices, you know that the determinant of AB is the same as the determinant of A times the determinant of B. But this is just the image of A under this map multiplied by the image of B under the same map. And this proves to us that the map is a homomorphism. Is that clear?
Yes.
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 Good. So we make a few observations. If you pick any, it's possible to have two different matrices that have the same determinant. So this map is not effective. So someone has the microphone on again. Who is it? So it's possible to find two different matrices which have the same determinant. So under this map will not be injective for that reason. Okay. it's not going to be 1-to-1. And for any any positive real number, it's always possible to find a matrix which has determinant equal to that real number, X, positive real number. So the map is surjective, but it is not injective. So we can call this, if you want to use the big words, we can call this an epimorphism. So here is an example of map that is not injective, but it is surjective. A homomorphism. So does that make sense? So the only thing we need to correct is here. This A and B come from the general linear group. They are matrices. A and B are matrices, so we should not be having R here. We should be having the general linear group in place of R. Any questions?
I have a question.
Yes.
What if, let's say, the determinant of A is negative, and the determinant of A times B will be a negative number? Will it be homomorphism?
But there's no problem with negative numbers. A set of non-zero real numbers include negative numbers.
Okay.
So non-zero means not zero. The only thing you kick out is zero. All the other numbers are retained. The negatives and the positives, they're all retained. So our set R star has negative numbers. So there's no problem with negative numbers. But they will still satisfy this property. Whether the sign does not matter here. If you multiply the determinant of any two matrices, the product of any two matrices will always be the product of the individual determinants. Doesn't matter whether the determinant is negative or positive. That doesn't count.
The last question.
Yes.
On this last statement, is this value X also in the general linear group?
No. If you want to check if a map is surjective, let's go back to the remember this thing. If you want to check if a map is surjective, you need to find that, check if the image of the map is the whole of H. So the image must lie in this set, right? That's why you have to pick an element from here and find out if it has a pre-image. So it turns out for that map, all the elements in R star have a pre-image. You can always find a matrix on this side, which gives you that as a determinant. So it's possible to construct such a matrix always. Did you do linear algebra too?
We did it.
Yes, so you must have learned about matrices. A lot of this is appearing strange to you, yet it should be familiar. Maybe you should find time and review the matrices. There's something I'm working on with some master students. When it's ready, maybe I can let you know. I'm thinking of having a seminar on linear algebra because it ends up being a problem a lot of time. So if when it starts, I can let you know. It will be free to join. So you just join when we run it. And if you don't make it, I will try to record so that you can do what? You can view it in your own time. So is your question answered now?
Yes.
So you have to refer to this diagram and the meaning of surjective. Surjective simply means the image is the whole of H. So we showed that if you pick anything in R, the set of non-zero real numbers, you can always find a pre-image for it, in the general linear group. That is, you can always find a matrix with that number as a determinant. Okay, so we proceed. So here is another example. We consider this map, which is from the group G to itself. It just picks every element in G and maps it to itself. So it maps X to X, where X is an element in G. So this map is called the identity map, and it's also a homomorphism because if you map XY to itself, it turns out to be the same. It's the same as the image of X under this map multiplied by the image of Y under the same map I. So it's a homomorphism. Now this I is a map. It's not a complex number. So I'm making sure I clarify this so that there's no confusion. I here simply represents a map. Now the reason we use I is because this is the identity map. You can use any other letter if you wish, but I is used likely because the word identity starts with I. So we observe that the map is injective. If I of X is equal to I of Y, by definition, X will be equal to Y. Therefore, the map is clearly injective. And every element of G is its own pre-image, right? So the map is surjective. There's no element that is left out. Are we together?
Yes.
Yes, we are.
So here we have a map that is surjective and it's also injective. So we can conclude that it's an automorphism. Automorphism here because the domain and the codomain are the same, G and G. The map is from G to itself. And since it's bijective, it's injective and surjective, we can conclude that it is an automorphism. So I hope that makes sense. So here is a map from the complex numbers. The complex numbers under addition form a group. So that's this C here represents the complex numbers under addition. And we are getting the map from C to the positive real numbers. The positive real numbers will form a group under multiplication. They will not form a group under addition, so don't try to use addition as a binary operation. You will quickly see that it doesn't form a group. So we define this map by you pick a complex number and you send it to its magnitude. The magnitude of a complex number is usually a positive real number. I think I may have made this should be C star, the non-zero complex numbers. So there should be a star here. So it should be the non-zero complex numbers under multiplication. I think I will correct that. So this should be C with a superscript here, star. Is that okay?
Yes.
Yeah, so we'll consider this as a group of non-zero complex numbers under multiplication. That one. And this is a group of positive real numbers under multiplication. So we can quickly check that this is a homomorphism. If you pick any two complex numbers, W and Z, the image of a product is just the magnitude of the product. And we know from our properties of complex numbers that the magnitude of a product of W and Z is the same as the product of the individual magnitudes of W and Z. So it's a It's definitely a homomorphism because phi of WZ is the same as phi of W multiplied by phi of Z, because this is just phi of Z from the definition here. So that's the homomorphism. So take note and don't forget, this is supposed to be C star. I'm repeating that so that there is no confusion at all. This should be C star, the group of non-zero complex numbers under multiplication. I'll correct it again before I share. So the map is definitely not injective because you can get two different complex numbers that have the same magnitude. In fact, you have an infinite number of complex numbers that have the same magnitude. For instance, if you're looking for complex numbers that have magnitude 1, or in the Agar diagram, all the complex numbers that lie on the unit circle have magnitude 1, and there's an infinite number of complex numbers on the unit circle. So it's definitely not injective because you can have two different complex numbers that have the same magnitude. And any, again here, this should be R plus. I think I must have been tired when writing this. So if you pick any X from R, the positive real numbers, so this should be R plus, the same thing as what you have up here. R and superscript plus. So any positive real number that you pick, it's always possible to find a complex number that has that magnitude. So if X is your number, you should be able to find a complex number that has X. As an example, you can pick this complex number Xi. There are many others as well.
Excuse, I have a question. Is the complex number, did you say non-negative or non-zero?
Non-zero.
Non-zero, okay, thank you.
Yes. So that should be C star. It should not just be C. I will correct it before. So the same thing here. Z, it should be C star. The reason we have to kick out 0 is because if you include 0, then the complex numbers will not be a group under multiplication. And since the binary operation we're using is multiplication of complex numbers, we must use the non-zero complex numbers. So this map is surjective because any element you pick, any positive real number you pick, you can always find an image for it. In other words, you can always find a complex number with that number as a magnitude. Are we together? So it's a surjective map, but it is not injective as well. So you can call it an epimorphism again, if you want to use the big words. Are we together?
Yes.
Okay, so let's move on to the next. So we have a theorem here. It says we have a map from G to H is a homomorphism of groups. So here we already told it's a homomorphism. You can make that assumption. So let E be the identity element of G and E prime be the identity element of H. Then the following can be true. We observe that the identity in G will always be mapped onto the identity in H. As long as it's a homomorphism, because we have been told it's a homomorphism, then this will always be true. The identity in G will always be mapped onto the identity element in H. Are we together? We shall prove this right now. Just let's go through the theorem. So the image of the inverse of H will always be equal to the inverse of the image of H. So H inverse is an element in G, but this is an element phi H, which is in G, in H rather. So the image of H inverse will always be the inverse of the image of H. Now this is the inverse in H, right? And this H inverse is the inverse of H in G. Because this element, phi H, is actually an element in H. So the inverse of phi H is simply the image of the inverse of H in G. And the image of X raised to N will be equal to the image of X raised to N. This follows from the property of being a homomorphism. You can prove it by induction if you must. So let's see if we have, so we are proving the first one. We want to prove this statement. So we use the following property. We try to get the image of E, and we know that E, by definition, can be written as E multiplied by itself. And now, since this map is a homomorphism, we've been told it's a homomorphism, we can split this into the image of E, the product of the image of E and the image of E again. But we, under this assumption, it means that because the image of E is equal to the image of E multiplied by the image of E. So basically this element is behaving like the identity in H. So it must be equal to the identity in H, because if you multiply it by this, you get the same thing. So it's behaving exactly like the identity in H. Remember, we said the identity in a group is unique. So anything that behaves like the identity must be the identity. So we conclude that the identity, this element, is an identity. So the image of the identity in G will always be equal to the identity in H, the second group. Yeah. Are we together?
Yes.
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 Good. So we now prove the second one. We need to show that the inverse of the image, I mean the image of the inverse of H is equal to the inverse of the image of H. So we already shown from the previous example, you know, that the identity in H is the identity in G rather is always mapped onto the identity in H. So we can write E prime is equal to the phi of E, which is equal to phi, and we know that the identity E can be written as H multiplied by the inverse. Again, this is just from the properties of a group. Every element has an inverse. So if you multiply an element by its inverse, you will always get the identity. This map is a homomorphism, so we can split this into the image phi of H multiplied by phi of H inverse. Now again, observe the following. You have multiplied this element by this element to get the identity. So that can only mean that this element must be the inverse of this element. Remember, the inverse is unique. Anything that behaves like the inverse must be equal to the inverse. So based on that, we can conclude that the inverse of this element must be equal to this one. And that's what we've written in the next statement. The inverse of H, the image of H, is equal to the image of H inverse. Because when you multiply the two, you get the identity. So this must be the inverse of this. But now that inverse is the inverse in the group H. So number 3 is left as an exercise for you. I should also switch the numbering so that they look the same. Here I have the Roman numbering. Yeah. Here I have this Arabic. I will
Question.
Yes.
How did you get the how are the E's, the multiplication of Q of E and the H inverse? How are they coming in?
So you need to understand the properties of a group. or rather you really need to find time and read the properties of a group.
Okay.
Anytime you pick an element in the group and multiply it by its inverse, you will get the identity element. So E, it doesn't matter which element you pick, any element you pick in the group has an inverse. And when you multiply it by its inverse, you will always get the identity. So I can always replace E by H inverse. The same way I can replace, if you think of this in terms of numbers, say under multiplication, I can always replace 1 by, say, 2 multiplied by 1 over 2. It's the same thing. Does that make sense? But now you have to
sense.
Yeah, you have to think in terms of groups, not numbers. Numbers are only one example. Not all groups will look like that. You will also have groups where these are matrices, so you can't have one over a matrix. A matrix, you will have to work with the inverse. So I just use the number because that is familiar, but this will not always be number. So you cannot write 1 over H here, because you don't know what this may be. Anything. It can be a matrix. It can be any number of different objects which are not numbers. Or for instance, it can be the dihedral groups. They are not numbers, so you can't write 1 over some element. You just write H inverse. So you just learn to play around with the properties of groups and use them to your advantage. So, and here we have used this property for groups and the inverse of an element in a group, and we have used the definition of a homomorphism here. Because we've been told this is a homomorphism, it means we can comfortably use this property. So this diagram tries to illustrate what is happening for a homomorphism. It says that the identity here is mapped onto the identity in H. So we have G on this side, we have H. The identity in E is always mapped to the identity in H. This is just the image of X. Now the image of X inverse itself is mapped onto this phi of X inverse. So the claim in our theorem is that the inverse of this element is just this. So hopefully this sheds some light on the statements in the theorem. So this is just illustrating what is happening in the theorem. So it's also possible to have other elements in G which are mapped onto the identity in H, which I'll see that shortly. That's possible. But what we can always guarantee, the only thing that we can always guarantee is that the identity in G will always be mapped onto the identity in H. And there will be situations for injective maps, for instance, where it is the only element that is mapped onto the identity in H. So we again use this example to illustrate the theorem. So consider this map defined by from R plus to R. So R plus, anytime you see this, it means the positive real numbers, and that's a group under multiplication. This is if it's R without anything, it's just the real numbers under addition. So the map is phi X is equal to log X. So to check that it's an image, it's a homomorphism, we just use the properties of logarithm. The logarithm of the product of X and Y is the same as the logarithm of X plus the logarithm of Y, which is the same as phi X plus phi Y. So this guarantees that phi is our homomorphism. but we make the assumption that we are working base 10. It doesn't matter which base. You just need to fix a base, and this will always work. Let me admit some people, I think, people hanging out class. So this map is a homomorphism. We have checked. So we know very well that the identity in this group, the group of positive real numbers under multiplication, is 1. And the identity in this group, the real numbers under addition, is 0. That is, we know. So we can check if this is, we can verify if the theorem actually works. So of course, under this map, the image of 1 is 0, because the logarithm of 1 is actually 0, right? So the identity is mapped onto the identity. That makes sense? And then the image of the inverse of 10 will be given by the logarithm of the reciprocal or the inverse of 10, which is -1. So -1 we know is the inverse of 1, but 1 is also equal to the logarithm of 10, which is just the image of 10. So since in this group, the binary operation is addition, so the inverse is just given as a negative. The inverse of 1 is the inverse of the image of 10. So the inverse here is usually considered additively. Use the additive notation because this group is an additive group. So I've admitted some people. I can now continue. So this just illustrates, using a simple example, that the inverse of the image of the inverse of 10 is equal to the inverse of the image of 10. So that will illustrate. The only thing is that you have to keep track of the notation. The binary operation here is additive, so the inverse is written as negative. So here is another map from the general linear group to R star. Again, we defined this earlier. We pick a matrix and send it to its determinant. We saw that this was a homomorphism. Now, the identity element in this group is the identity matrix, right? Which we shall call I, capital I. And the identity element on this group of non-zero real numbers under multiplication is 1. So we can check that the identity matrix has determinant 1. So the identity matrix is mapped onto the identity in R star. And again, for the inverses, if you pick any matrix from the general linear group, the image of the inverse is given by the determinant of the inverse, which is the same as 1 over the determinant of A, which is actually the inverse of the image of A. Because 1 over the determinant, since you're working with real numbers, the image of any real number is just a reciprocal. The inverse, rather, of any real number under multiplication is just a reciprocal. Any positive real number. Or any non-zero real number, not positive. Any non-zero real number, the inverse will be just a reciprocal. That's why we have this here. So again, this verifies what we said about the theorem. So you cannot use this as a proof for the theorem. This is just to show you some concrete examples where we are verifying the theorem, but these are not proofs by any measure. So never write this as a proof. You will not get any marks. The proof, we have done it. You have seen the proof. So anytime you're asked to, if you are to write out a proof, you use the proof that we showed earlier. Now, again, some people are trying to join. Let's admit them. So is this clear?
Yes.
So we now define the kernel of a homomorphism. So if you have a homomorphism from G to H, here we simply assume G and H are groups. I think at this point we work with that assumption. Anytime we talk of a homomorphism, these must be groups. So the set we refer to as the kernel is a set of all elements in G that are sent to the identity element in H. Remember, we used, anytime we have two groups, we use the small letter E for the identity in G and the E prime, small letter E prime, as the identity in H. So the kernel is simply all elements in G which are mapped onto the identity element in H. So you can see in the diagram, it's if you can find all the elements here which are mapped onto the identity, then this is a kernel. So the kernel is a subset of G, or the domain of the map. So the kernel is a subset of G, and it's possible for the whole of G to be the kernel. The first example of a homomorphism actually sent all the elements in the domain to the identity, in the codomain. And therefore, that was an example where the kernel was the whole group. That can happen. That was a trivial homomorphism. Now, it can also be just a subset. Then there are situations where the kernel can consist of only the identity element. And that is one of the elements that is guaranteed to be in the kernel anyway, because we saw that, I can go back here, we saw that the identity is always mapped onto this identity. So this element, the identity in G, will always be in the kernel. So it can be the only one, or it can have other elements in the kernel. We should see some examples. So but I have some examples here. Okay, yeah, I think that's fine. So let's look at this theorem. We have a map from G to H, and it's a homomorphism. We say that phi is injective if and only if the kernel consists of only the identity element. So in the proof, we shall take E prime to be the identity element in H. So if a kernel consists of only one element, and that's the identity in G, which is what the elements that must always be there anyway, then we say that the map will be injective. Let's see if we can prove this. So there are two things. Since we have it's supposed to be a logical equivalence. So it's if and only if. So we have to show two directions. One is assume that the map is injective, and show that if that is the case, then the only element in the kernel will be the identity element. And then we prove a converse, in which we assume that the kernel contains only the identity element, and if that happens, the map must be injective. So let's start with the first one. Suppose the map is injective, and X is an element of the kernel, right? So let's pick something from a kernel and see what else can it be. So if it's in the kernel, then its image must be equal to the identity element in H. But we also know that the identity element in G is always mapped onto the identity element in H. So this again is equal to the image of the identity element in G. So, but we know that the map is injective. So if the map is injective, phi X being equal to phi E means that X must be equal to E. That is because the map is injective. So what this says is that if you pick any element in the kernel, it can only be equal to the identity element. And therefore the kernel consists of exactly just one element, and that is the identity element. Because if you pick any other element, it turns out to be just equal to the identity, using the fact that the map is injective. That's okay?
Yes, we
You
can
hear
hear
me?
you.
Yes, yes.
Yes.
Good.
Yes.
So,
Yeah, I can hear you.
Yes.
good. So we prove the converse. So if suppose the kernel consists of only the identity element, so let's pick any two elements, X and Y from G. Then we can check the following. If phi X is equal to phi Y, then it means if you post multiply both sides by the inverse of phi Y, you will end up with the identity. So I multiply phi Y inverse and phi Y inverse on both sides. The inverse, so this will still be phi X multiplied by phi Y inverse, which is this. And this side would be equal to the identity in H. Now it's the identity in H, which is E prime. Now, since this is a homomorphism, this inverse can jump back in using the properties of a homomorphism. There's a theorem we proved just a few minutes ago, which says that this inverse can jump back in. And again, since this is a homomorphism, you can bring these two back together, X and Y inverse in the brackets. So that means if so what we have basically shown here is that the image of XY inverse is equal to E prime, and that means XY inverse is in the kernel, right? But we have made the assumption that the kernel has only one element, that's the identity. So anything that is in the kernel in this case must be equal to the identity. Yeah, so if that is the case, if anything in the kernel is equal to the identity, then XY inverse will be equal to the identity element. And then you can use post multiply both sides by Y, which says X is equal to Y. So that shows you that the map is injective. So we have proved that if phi X is equal to phi Y, then X must be equal to Y. And that means the map is injective. So if the kernel contains just the identity element, then the map is injective. And also if the map is injective, the kernel will only contain the identity element of G. That makes sense?
Yes, it does.
Yeah.
Yes.
So here is the next one. Some examples to illustrate what we have just done. So we have seen this map several times now. This map which sends the matrix to the determinant. It's a map from the general linear group to the non-zero real numbers under multiplication. So to find the kernel of this map, we need to find all matrices in the general linear group that are mapped onto the identity in R star. The identity in R star is 1, so you need to find all matrices that are mapped onto 1. What that simply means is you find all matrices whose determinant is equal to 1. So definitely this is not injective because the kernel will not be just the identity matrix. The identity matrix is one of the matrices which has determinant 1, but there are so many other matrices also which have determinant 1. So this kernel consists of all matrices that have determinant equal to 1. So since the kernel does not consist of only the identity element, then this map is not injective. Based on the theorem, we can conclude that this map is not injective. Here is another example. Here we have a map from R plus to R. R plus is the positive real numbers under multiplication. R will be the all the real numbers under addition. So we already saw this map to be a we saw that this map is a homomorphism earlier. So we want to check what is the kernel of this map. So the kernel of this map is simply the set of all elements here which are mapped onto the identity in R under addition. The real numbers under addition, the identity is 0. So the kernel simply means we look for all the positive numbers that are mapped onto 0. But the map here simply means the logarithm, right? So we look for all numbers whose logarithm is 0. So if x is in the kernel, its logarithm must be equal to 0. And that means x should be equal to 10 raised to 0. And the only number that satisfies this is 1. There's no other number which will satisfy this property. So again, we assume the base is 10. You can work with any other base, it will still work. But you have to fix a base for you to proceed. So we fix the base to be 10. So since we can't find any other number that satisfies this property, it means 1 is the only element in the kernel. So there's no other element in the kernel of this map except the identity in R plus, the positive real numbers under multiplication. And based on the theorem, since the kernel consists of only the identity element, we can conclude that the map phi is injective. Are we together?
Yeah.
So here we have shown some examples of how to find the kernels of a homomorphism and use that to determine whether the map is injective or not. Today we are really rich with theorems. I think we can do one more. Ama bado muko na bidii?
Uwe.
Kuna bidii.
Imeisha bwana.
Imeisha. Umekunywa uji bwana?
Hizo.
Imeisha jamani.
So we could stop there.
Tuendelee.
Tuendelee. Okay. So let's
No, but.
Wewe, hey.
No.
Let's do this one as the last one. We'll do this as the last one.
Acha tu digest hiyo kwanza.
Yes.
Okay. Do you have any questions on the previous one? So tomorrow we will start from this. This page. Yeah, we'll start from here tomorrow.
Okay.
Naona mmeogopa kidogo. Mmekuwa kama Maniu.
Unachoma.
Usiongelee Maniu.
Maniu. Manchester United.
Yes, let me stop recording. You can ask any questions now.
Sure, you forgot to share the slides from the previous lecture.
It's the same set. I just need to clean up. As you noticed, there are some errors in this one. So when I clean up the errors, I will share.
You have not said as much as.